one. You barely need one, but I'll give it anyway if you don't mind. And,
hey, Sam, how come I needed one but Russell doesn't?
Oh, well, you didn't need it either. I'm going to shut up here in just a second. Okay. So anyway, let's see. So what should I say? Russell earned his PhD at Berkeley. He was a postdoc at Toronto. He's subsequently been at UC San Diego pretty much all the time. There was a 5-year stint at the Institute for Advanced Studies. He's been a Guggenheim Fellow and a Simons Investigator. He received the inaugural Road Prize in 2013. He's well known for many important contributions in pseudo-randomness, XOR lemmas, and of course proof complexity, among other areas. And he's also a developer of the ETH and strong ETH, which I suspect we'll hear something about in this upcoming talk, which is hypotheses about satisfiability and their consequences. So Russell.
Okay, thanks. So yes, today I am going to talk mainly about the exponential time hypothesis and strong exponential time hypothesis. Both of these were joint work with Mohan Paturi at UCSD, and a bunch of other people were involved. So I'm going to thank Mohan. Mohan was involved in everything. So I'm going to thank Mohan in advance and try to acknowledge other people as they come up in the story. So if there's a P that's left as an initial, that stands for Paturi. If there's an I, it stands for me. Okay. Right. So Cook's theorem says that NP-complete problems, and satisfiability is like the paradigmatic NP-complete problem, are the hardest problems in NP. Except it really doesn't say that. Because when you look at things, one is, I seem to be echoing.
Seems to be okay now.
Okay. If you look at things quantitatively, different NP-complete problems, if one NP-complete problem has a great algorithm, then the others have great algorithms. But if you look at their exact time of the best known algorithms, these are all over the map. Okay, they're all exponential, but they're different exponential functions and exponential in different quantities. Okay, so and if you look at average case time rather than worst case time, or approximation algorithms or heuristics, they're all really very different as far as these things are concerned, at least as far as we know. So why did I start thinking about satisfiability? I'm in complexity theory, so thinking about NP completeness is very natural. But when I was co-teaching a course, this is with Steve Cook. I presented this at a workshop in honor of Steve Cook, so I didn't have to say which Steve I was talking about. One topic of the course was kind of like a robustness of the linear time hierarchy. And I don't need to really define what the linear time hierarchy is, but the idea was that even though linear time is not so well defined, if you look at non-deterministic variance, because it depends on the exact model, things like non-deterministic linear time are much more well defined. I said, well, let's at least we can't prove P not equal to NP. We can't even prove NP is different from exponential time. Let's at least prove that there's some kind of non-trivial separation of classes. And thinking about this kind of non-deterministic linear time, said, well, that's kind of robust class. Let's at least show that non-deterministic time linear isn't equal to deterministic time exponential. And that's ridiculous to think that every exponential time computable problem would have a linear time certificate, linear size certificate. So, and especially one that's not verifiable in linear time. So when you like look at what almost complete problems for linear time, for non-deterministic linear time, SAT is pretty much complete for non-deterministic time. There's like a log factor overhead. So if you can just give a 2 to the n over log n algorithm for a SAT, that's still exponential, right? That wouldn't be a big deal as far as like NP completeness goes, but it would show that non-deterministic linear time is strictly contained in deterministic exponential time. So I'll just find, and it won't be the world's most revolutionary algorithm, but from complexity point of view, it would be a pretty big deal to have a SAT algorithm that ran in time 2 to the n over log n.
Sorry, Russell, did you want to put NP in D time 2 to the order n? What you wrote there is known.
This is meant to be like strict subset.
Strict subset. Oh, I see.
So it's known that it's contained in, but not known that the inequality is, the containment is strict. So as far as we know, every problem in E could be in non-deterministic linear time. Now, you have to say, okay, so maybe that's not true if you're restricted to like K-tape Turing machine. I wanted it would be more robust notion of linear time. So I guess there was, does that answer your question?
Yeah, I just didn't realize that meant proper containment, that's all.
Okay, yeah, so the point is, the containment is trivial, it's the properness, I couldn't get PowerPoint to put a little line through something below the containment. So okay, so what I mean here is proper containment because it doesn't have a little line underneath it. Okay, so anyway, to do this, all I have to do is come up with a SAT algorithm that worked a bit better than exponential, and surely there's such an algorithm, right? And also said, well, you don't have to actually show it in the worst case for SAT. If you look at like, if we could just show non-deterministic time 2 to the n is strictly contained in deterministic time 2 to the order n, then that would be enough. Actually, 2 to the order 2 to the n, that would be enough. So you could actually like look at some very structured instances of SAT and come up with better algorithms for that. And actually, I don't have a reason why you couldn't carry that out for the structured instances of SAT. So anyway, so I went around asking people like Toni about whether they thought there were better SAT algorithms, and she pointed me to Bart Selman, who was a PhD student in the department in Toronto, who was actually really interested in better SAT algorithms, because he was not just he was in the AI group, and he was actually using SAT algorithms to solve real world problems. A little bit ahead of his time on this. And so he was coming up with positive approaches to SAT solving that weren't provably fast in the worst case, but seemed to be working on a lot of interesting SAT problems. And so I became kind of aware that there was a community developing of people who were using SAT algorithmically and improving the time for SAT algorithms on real world instances that came from different applications. And in fact, Bart was actually really interested in the theory of SAT algorithms. He had a big binder of SAT and other algorithms for SAT and other NP-complete problems. And I kind of looking through, I was able to borrow Bart's binder. And looking through it, there were a lot of really clever ideas that a lot of very smart people had come up in improving the algorithms for these problems already. And they were all really good ideas, but they were all still kind of exponential time algorithms. None of them, were suitable for separating these complexity classes. But, and sort of like said, to get a better algorithm in this direction, I have to kind of like be a little cleverer than all of these very clever people. And the reason why I'm mentioning Bart's binder, because maybe Bart will, is still interested in this area, and maybe he's listening. So Bart, if you want your binder back, send me email, because I still have it. Okay. So, okay. So I was still optimistic about finding sub-exponential algorithms for one of these natural NP-complete problems. So I like filled up over the next few years, I filled up a lot of notebooks with different failed attempts to beat the known algorithms. And it was kind of like my go-to problem when I couldn't think of anything else to work on, because it was kind of, I knew it had the feeling of being hopeless, but still it kind of like generated ideas and kept me busy. So, but while I was working on it, these heuristic SAT solvers were getting really, really good. So on the one hand, they were kind of that area that Bart was one of the early adopters for, had kind of taken off. And I know people looking back say, oh, the 90s was kind of primitive as far as SAT solving goes, but there was already some pretty impressive results from the heuristic point of view. Okay. On the other hand, we sort of also were becoming more and more convinced that these heuristic methods wouldn't solve the problem in the worst case, because and I'm gonna get back to this later in the talk, hopefully. Most of these heuristic methods were based on resolution proofs, on an unsatisfiable unsatisfiable formula. They produced a resolution proof, not just some kind of certificate, but a certificate of a form that logicians understood pretty well, called a proof system, probably known to most of this audience, called resolutions. Very simple. And we were also getting the theory area was getting sharper and sharper lower bounds on resolution proofs. Okay? So like Beam, Karp, Potassi, and Sachs around the time I'm starting thinking about or continuing thinking about these problems, proved an exponential lower bound for, say, random SAT formulas for resolution. So we know that these algorithms, even though they're doing really well on instances that came from applications, had some kind of bottleneck for random instances, and there were many other instances based on the proofs of theorems, in fact. Okay, so Jack was talking about these theorems that you can prove hold for every input, that there exists some kind of object that you can verify. Often that verification is very local. You can write down the verification as some kind of clause, and then you're like saying it's unsatisfiable, that there's no solution, which means that you're sort of like every possible solution corresponds to this small set of small clauses. You take the conjunction over those this is not an example, this is not a witness, this is not a witness, this is not a witness, and you take the conjunction and you get an unsatisfiable formula. And so like if you show that unsatisfiable formula has large refutations, and saying proving the theorem is at least a little bit non-trivial. Okay, so and there were lots of these kind of theorems where the translation was known to take exponential time for SAT solvers. So random instances took exponential time. Instances that were kind of cleverly designed take exponential time. So why were these algorithms working so well? Anyway, so fortunately, I was very close to success at designing a better SAT algorithm. But unfortunately, what that means is that the better SAT algorithm was being designed at the office next door to mine by Mohan, who I'm going to mention by name here, Pavel Pudlak, and Francis Zane. And then in follow-up work, Mike Sachs joined them and got an even further improvement using similar techniques, using a sophisticated refinement of the same techniques. And so they showed that, yes, you can beat exhaustive search, but they still only beat it by an exponential amount, but an amount that sort of decreased with k. And still left an exponential time, even for k equals 3. Okay, so the original paper got a savings over exhaustive search of 2 to the n over k, and then the follow-up got a savings of something like 2 to the 1.8 n over k. Okay. And their algorithm technique was simple, but their analysis was very nice. Okay, so the simple, you like do something that's just one step short of picking a random assignment. You pick a random assignment, then as you're setting it in a random order, as you're setting those literals, you see if there's unit propagation, and if there is, then you don't randomly set the variables that are subject to unit propagation. And they don't phrase it exactly this way, but I think it's equivalent. Okay. So at some point, I switched gears from trying to come up with better SAT algorithms and said, maybe it would be interesting if we couldn't design better algorithms, if this was the limit. And really, I said, like, it's kind of paradoxical in my thinking. Maybe just because I'm this shows a defect in my mental state, but the more success there was in interesting approaches to SAT and improvements using interesting new techniques, and for the and all these clever results in this binder that Bart had given me, and the more really clever heuristics people were using that we knew wouldn't work in the worst case, the more it seemed like that there was an inherent barrier to getting progress in the worst case, or at least possibly an inherent barrier, because it seemed that over time people were spending a lot of intellectual effort trying to get improved SAT algorithms, and yet the algorithms that we had were still exponential time. And in fact, for k large, they weren't even that much better than exponential, than brute force search. So, so what we decided to do is think about, can we quantify, this question, make precise this question of how much better can you do than exhaustive search, and use complexity theory to like systematically explore the consequences either way of whether or not we can do better. So that's what motivated the exponential time hypothesis, and later the strong exponential time hypothesis. So if you look at the time for the PPSD algorithm, it's of the form 2 to the Cn still, and we could define the best exponential time algorithm as the infimum over all the set constants c, so that k sat is in time 2 to the cn, and call that result ck. So it's possible that ck is 0. Ck exists, but it's possible that ck is 0, meaning you have a strictly sub-exponential time algorithm, or at least like a series of exponential time algorithms that improve the exponent arbitrarily. So, and the constant that you got from the best algorithms was something like ck is at most 1 minus 1.8 over k. Okay. So pretty good, pretty reasonably small when k is 3. When k is 100, not so small, pretty close to 1. Okay. And that was the best, that was kind of like the frontier, the best known value for ck at the time. And it's actually still, for a large enough k, is still pretty much the best known. Okay. So so what we said, well, the hypothesis, sort of the whether or not we could carry out this plan of finding a sub-exponential algorithm for SAT, or whether there's a strict limit, is really a matter of whether these constants are equal to 0 or bigger than 0. Since that the exponential time hypothesis is that the constant for 3 SAT is actually bigger than 0. Now, if the constant for 3 SAT is bigger than 0, then clearly the constant for 4 SAT is bigger than 0, 5 SAT, and so on. We can this series is going to be bounded up or bounded by 1, so it's going to have a limit. As far as we know, using this formula, the limit could be 1. So let's define C infinity to be the limit of this series of constants. And it might be 1, or it might be strictly less than 1. Or it might be 0 if the exponential time hypothesis is false. Okay. And please interrupt with questions at any point. Okay. So, and I said, as far as we know, the best constants approach 1 as k grows. So that's the strong exponential time hypothesis, that limiting constant is 1. So they get to it gets, as k increases, the algorithmic time requires gets closer and closer to brute force search, to exhaustive search. And Vias and Williams even give a super strong exponential time hypothesis that, and this is kind of strong, is saying that the form that the PPSZ algorithm took in the savings is really the right one. It's 1, so ck is 1 minus theta 1 in k. And this seems like a very daring hypothesis, but it turns out that a lot of different SAT algorithms after PPSZ, after we started talking about ETH and strong ETH, all came up with really clever approaches to SAT, and they all had savings that were roughly 1 in some constant over k. And they're using very different approaches to doing that. So so there does seem maybe there's something inherent, at least easy algorithms give you savings 1 minus 1 in k. Sorry, give you constant 1 minus 1 in k, savings 1 in k fraction. And they also, in the same paper, they showed that they introduced this hypothesis. They showed that it's false for the average case complexity of satisfiability. Okay, so what do I mean by formulating these as hypotheses? I'm being careful not to use the word conjecture for them. What makes these hypotheses really interesting is, I think, if you look a conjecture like P not equal NP, I'd be kind of surprised if P turned out to be equal NP. Okay, it's, until we prove it, we could still be wrong. But complexity theory is sort of like, if P were equal to NP, most of my papers would become obsolete. Okay, so I'm really kind of betting my career, the significance of my career, on P not equal NP. So that's kind of like a strong willing to gamble. These hypotheses are meant to be more 50-50. They could be true or they could be false, and I don't know which. I don't think anybody has a really good idea about whether these hypotheses are true or false. So if you ask me to, depending on the day, if you ask me to give odds on the exponential time hypothesis, it's about even odds. Strong exponential time hypothesis, it should be, it's clearly like less plausible than the exponential time hypothesis, but not zero probability either. Okay, and so what makes them interesting is that they sort of like are better ways of splitting the probability space about complexity into equal size, they could be true, they could be false categories, and they have really interesting consequences whether or not they're true or false. So it also bears in mind, you can write papers about if the exponential time hypothesis holds, then these interesting things happen, and then you can turn around and write papers that say if the exponential time hypothesis fails, these other interesting things happen. And then you can try like put on your Ryan Williams hat and try for a win-win argument saying, well, if it holds, this happens, and if it fails, this happens, so this happens. Okay, so so the exponential time hypothesis says that that the complexity of k-sat or 3-sat is exponential. Why did I pick 3-sat? Well, it turns out that at the time we said, well, 3-sat is kind of like hard for this natural class of NP complete problems, constraint satisfaction problems. So if you came up with a sub-exponential 3-sat algorithm, it'll turn out that you can come up with a sub-exponential k-sat algorithm for arbitrarily large k, and then you can translate that to showing that you can also solve independent set or colorability or lots of other problems in sub-exponential time. So it was like interesting because if the exponential time hypothesis were false for 3-sat, it's also false. The corresponding thing is false for a lot of different NP complete problems, natural NP complete problems. So let me try to be more precise about that. So what do I mean for a sub-exponential time algorithm for an arbitrary NP complete problem? Do I mean like sub-exponential in the number of vertices, sub-exponential in the number of edges, in this total bit description? So we have to be a little bit careful in saying what we meant to be sub-exponential for. So what we want to do is say it's better by a super polynomial amount than exhaustive search. So we actually have to define sub-exponential for search problems rather than decision problems. And so within a search problem, you have bits to describe what you're searching for. Exhaustive search is exponential in that number of bits times some polynomial in the input size. And so we said, let's look at, for each problem pi, look at the smallest constant c so that there's a 2 to the cn times some polynomial in the total input size, where capital N algorithm, where capital N is the number of bits to describe a solution. And so ETH for that problem is to say that this constant is bigger than 0. Strong ETH for that problem is the constant equals 1, or sometimes, with k-sat, we want to like take the limit as k goes to infinity. So we have a sequence of problems. We say the limiting constant for the sequence equals 1. Okay, and so this is very similar, distinguishing between the size of what you're searching for and as one parameter, and the size of the instance as a different parameter, and analyzing the complexity two-dimensionally is in that sense, we're following the parameterized complexity notion of Fellows et al. And there are actually lots of really deeper connections between parameterized complexity and this kind of study of exponential exact complexities for NP-complete problems. So what we showed in our paper is that first, if 3-sat is just a typical instance of a kind of sat, 4-sat is equivalent, 5-sat is equivalent, and so on, as far as having exponential time. Okay. And this took some actually to show the equivalence wasn't completely obvious, and I'm going to talk about that in a minute. Okay, and then we showed that also implies that the exponential time hypothesis is true for many natural NP-complete problems. Okay, so actually, since then, the dichotomy theorem has been proved, and with all the building on all the dichotomy theorem that shows that every CSP, there's kind of a natural characterization of when a constraint satisfaction problem on a finite domain is NP-complete. Building on that, Johnson, Lager, Kvist, and Roy showed that, in fact, for any NP-complete constraint satisfaction problem, the exponential time hypothesis for that problem is just the same as the exponential time hypothesis for 3-sat or whatever other problem you want. So it's really, really a robust notion, okay, more than we had thought. So if the exponential time hypothesis is true, not just satisfiability, but every NP-complete constraint satisfaction problem requires exponential time. And if it's false, that means that all constraint satisfaction problems can be solved faster than exponential time. So we could have picked coloring, and it would have worked out the same. We could have picked independent set or clique, and it would have worked out the same. Might have been a lot more work to get there, but in the end, they're all equivalent. Okay. Why does it require work to show this? Why can't we just plug it into the standard reductions that we get from NP-completeness theorem? It's because we really want to be exponential in the size of the solutions. Okay, and when you give a standard NP-completeness proof, the size of the instances can grow up polynomially, and so that changes the notion of being exponential versus sub-exponential. Okay, but if you look at the standard reductions between standard problems, they're almost all linear time reductions, and that's true. However, it still doesn't preserve exponential versus sub-exponential time in the sense that I was talking about, because usually what linear time means is linear in the number of variables plus the number of constraints. So you have like one gadget that introduces some new variables for every original variable, and another kind of gadget that introduces some new variables for every kind of constraint. And so then sub-exponential becomes sub-exponential in the number of variables plus the number of constraints, but the number of constraints can be an arbitrary function of the number of variables, arbitrarily much larger than the number of variables. So these don't really preserve having even these linear reductions don't preserve having a sub-exponential algorithm in the sense that we're interested in. So, so what we showed is that for satisfiability, you can make the number of constraints a linear function of the number of variables without loss of generality. So precisely, we show that the sparsification lemma, and this was improved in subsequent work by with Calabro, based on a suggestion of Mike Sachs's, so that for every k in epsilon, there exists a constant c, so that we can reduce k-sat in n variables to k-sat on the same number of variables and a linear number of clauses in time 2 to the epsilon n. So the constant c depends on epsilon and k. Originally, it was doubly exponential. In the improved work, it's exponential. So then we can, now that we've made the number of constraints or clauses linear in the number of variables, now we can plug in the standard reductions and they work just fine. Okay, so I'm going to give you like a quick overview in a minute. I want to like show a simpler example that was actually discovered independently around the same time for a simpler problem, the independent set problem. So they showed, Johnson and Szegedy showed to how to reduce independent set on an n vertex graph to independent set on an n vertex graph with a linear number of edges, or with multiple n vertex graphs with each with linear number of edges in time mildly exponential, 2 to the epsilon n for an arbitrarily small epsilon. And the idea is to pick that constant c that you're shooting for sufficiently large. Okay, the larger we pick c, the smaller the epsilon's going to be. And we'll just branch, if there's a vertex of degree c, we branch on whether or not to include it in the independent set. This is like the first algorithm that you'd think of, maybe the second after exhaustive search. First backtracking algorithm you think of for independent set. Okay, so if there isn't such a vertex, you're done. The graph has a linear number of edges. If there is, then you're making lots of progress, because on one branch you remove one vertex, that's a little bit of progress. On the other branch, you eliminate at least c vertices, that vertex and all its neighbors. Okay. Okay. So and you can use this to bound the number of total number of graphs that you could get in the whole branching process as n choose n over c, which as c grows becomes 2 to the epsilon n for small epsilon. For k-sat, we can do a similar thing. That's our proof is doing a similar thing for k-sat. There was kind of a mindset barrier that we had to get through in order to come up with this sparsification technique, okay? Or at least for the analysis. Because I guess like initially we're thinking, oh, what we want to do is make the graph sparse, right? So so we want to get, having more clauses is bad for us. But what we're really doing in this argument is saying, if the graph is dense, we can use that in a, if the graph has a lot of edges, that's going to help us design a faster independent set algorithm. So here, we want to say, if we've got lots of constraints, lots of clauses, and especially small clauses, that's going to help us prune the search a lot. So it's not that we want to get rid of clauses, is that we want to actually create small clauses as much as possible. Okay, so it's not, and then utilize those small clauses that we create. So if the original formula is dense, we want to say we can actually exploit that and get faster algorithms while it stays dense. And it'll be bad when it becomes sparse, but then we're shooting for a reduction rather than algorithm. So we can just say, oh, instead of saying that's bad, we say that's also good in a different way. Okay. So, so our goal is actually to create many small clauses, as many as possible. And here's how we'll do that for 3-sat. We'll have 3 levels of branching rules. Okay. One is the best so first, we always remove clauses. If one clause contains another clause, we remove the larger clause because it's kind of redundant. So that's an obvious thing to do. Okay, so as we're creating clauses, if they subsume other clauses, we remove the subsumed clauses. So so if we've got a lot of really small clauses, if you've got lots of 1 clauses, those are just variables, we're already done. If we've got lots of 2 clauses, then they have to a lot of those 2 clauses have to contain the same variable, branch on that variable, and that's creating a lot of 1 clauses setting variables, and that's immediately good. Okay, so if we have a lot of 2 clauses containing the same variable, we branch on that variable. In the true case, we just get that 1 variable. In the false case, we actually get more because every variable that appears within a clause now has a defined truth value. Okay. If there aren't a lot of 2 clauses, then we look at the 3 clauses. And the best thing is if we have a 3 clause that contains a lot of 3 clauses that contain a pair of variables x or y. Okay. So if they do contain a lot of these literals, we're going to branch on not is x true, is y true. We're going to branch on whether is x or y true. And in this case, in the true case, we just get 1 2 clause. Okay. But in the false case, we get a whole bunch of variables. Okay. So like the true case, it doesn't seem like we're making progress at all until we think that we really want to introduce small clauses, and 2 clauses are pretty good at that. Okay. And so then the fallback is if there are many 3 clauses that contain 1 variable, but there aren't a lot of 3 clauses that contain any pair of variables, then we branch on that 1 variable. And in one case, we get 1 variable, and in the other case, we get a whole bunch of 2 clauses. That's going to lead to the better kinds of branching in the future. Okay. And I'm not seeing any, please stop me and ask questions, although I need to turn on. So, so then the argument is very similar, for the time analysis, it's very similar to the Johnson-Szegedy analysis, except we have to analyze the effects of these rules separately. Rule 1, that's very similar to the Johnson-Szegedy, because whenever we get, we either get 1 variable or a whole bunch of variables. Okay. Actually, I think I skipped over. So we can say the number of false branches for rule 1s or rule 2s, both of those create a whole bunch of variables, and we can create at most n variables total. So that bounds the number of false branches for rules 1 or rules 2. It also bounds at least marginally the number of true branches for rule 3. Then whenever we get too many 2 clauses, we'll be guaranteed to be able to apply rule 1. So we'll make sure that no variable ever appears in too many 2 clauses. And this is going to bound the number of 2 clauses that we could ever create, because if we create too many, then we'll use rule 1 a lot, and then rule 1 will set all the variables along most paths. Okay. And that's going to bound the number of true branches for rule 2 and false branches for rule 3. So when you put all these things together, you can show that the total number of branches until we run out of rules to apply and the formula is sparse, is going to be just mildly exponential. Okay, and so you can generalize that to k-sat. Instead of 3 rules, we'll have roughly k choose 2 rules based on the size of clauses up to k and the sizes of the sets of variables that we're going to branch on. Okay, and from when you sparsify, so if you like combine all of these things, so it's not only true for SAT that we can do sparsification, but we can do sparsification for any kind of NP-complete constraint satisfaction problem. Because when you take any constraint satisfaction problem, it's really easy to map it to k-sat. We can sparsify the k-sat instance that we get, and then use the reductions that we get from the dichotomy theorem that are just linear in the number of variables and plus constraints to map it back to an instance of the original problem pi. And that's going to have both a linear number of variables and a linear number of constraints. So, so we can take any constraint satisfaction problem and reduce it to the same constraint satisfaction problem with a linear number of constraints in the number of variables. Okay. And so that really is kind of like an intuitive, is a hard, non-intuitive way of proving something intuitive, which is that if this exponential time hypothesis is true, what it says is that the hard instances of a constraint satisfaction problem are those with a linear number of constraints. Okay. And if you look at instances with more than a linear, more than proportional number of constraints to variables, those tend to be very over-constrained, called over-constrained instances, and become easier. And especially for like random instances, seem to be of CSPs are hardest at there's going to be for each CSP a fixed constant density threshold where it goes from satisfiable to unsatisfiable, where it becomes the hardest. On the other hand, we can also show that ETH implies that the hard instances are not too sparse. They're also not going to be under-constrained instances. So what we show is like, look at SAT with no bound on K, but where we're saying the number of constraints is at most D times N. We were able to give use Schiller's method to give an improved algorithm for any fixed D, but we also showed that as D increases, the constants that you get are the same as the constants you get in the limit for k-sat. So, exponential time hypothesis for k-sat is equivalent to the exponential time hypothesis for a linear number of constraints sat, but also for the strong versions of these, the limiting constant for one is 1 if and only if the limiting constant for the other is 1. And it also follows from this that, okay, with a little bit of work, that means that the densest instance, the hard instances for k-sat must have a density that's an increasing function with k. Okay. Now I think we get like that the hard instances for k-sat must be at least like linear in density or polynomial in density. Density must be polynomial in k. Really intuitively, it should be exponential in k. So I would challenge you to like think about reasons why that density must grow exponential in k. And I am really far behind. Okay. So another consequences of the exponential time hypothesis is very intuitive. Say, okay, we wanted to say that NP-complete problems are not all equivalent quantitatively. These notions of the constants for each problem give us a way of formalizing that. We were able to show that the constant for k-sat is less than the limiting constant by a 1 minus omega 1 in k factor. And it follows then that if the exponential time, they could all be 0, but if they're not all 0, that means that these constants ck are strictly increasing infinitely often. And so that is a formalization of the intuition that k-sat becomes harder as k increases. Okay. So what I'd like people to work, one thing I'd love to happen is, we show sort of in the limit k-sat becomes harder, but we don't have like a bound that says that each k plus 1 sat is strictly harder than k-sat. Another thing that follows from ETH is not just the hardness of worst case satisfiability, but even some very special cases of satisfiability become exponential, are going to be exponentially hard, like unique satisfiability. So even if you're given a promise that there's at most one satisfying assignment, finding that satisfying assignment is going to be exponentially hard. And in fact, it's going to be in the limit equally hard as the constant for the exact exponent for unique k-sat is equal to the constant for the general case. So that shows that we can't really say that we're going to get sub-exponential time algorithms based on the structure of the solution space, because I think unique solution is the simplest non-degenerate solution space that you could think of. So we could say, well, how about instances, can we come up with better algorithms, when we have restrictions on the instances that imply that there are better algorithms, are we going to be able to further improve these algorithms? A lot of people have really nice results saying no. Like Luxenov, Marx, and Sarab show that if the strong exponential time hypothesis is true, you can't, if we have a bounded tree width graph, a bound on the tree width of the graph, then you can usually solve problems in exponential time in the tree width. And what this says is that you're not going to do much better than that for bounded tree width graphs. We also have a lot of ways of taking complexity results about NP-complete problems and showing, using them to show hardness of problems that are in polynomial time. Okay. And this kind of adds to a growing area that we'll call fine-grained complexity. We made up that name for Simon's program a few years ago. You can say like other strands involved, like hardness based on the k-sum conjecture introduced by Gajantam and Overmars in the context of computational geometry, and work by Vasilevska, Williams, and Williams on equivalence of many triangle problems. And so like these different basic hard problems, the versions of the exponential time hypothesis kind of joined together with some of these other lines of work converge into an area that's really exciting, because it's giving, showing that lots of the textbook algorithms just can't be improved, or if one could be improved, that would have ripple effects into lots of the others, into these kind of basic core algorithmic challenges. Okay. So in fine-grained complexity, kind of you're looking at generic, reductions between problems that preserve almost exactly the time that the best time that known for the algorithms, for algorithms between the problems. And I'm gonna like really slide over this quickly because I don't I have only 5 minutes left. So I'm just going to give one quick example that relates ETH to this K-sum conjecture. This is an example due to Petroscu and Williams that shows that if the exponential time hypothesis is true, the K-sum problem is like given K sets of n numbers, is there one number from each set that sums to a given target? And what they show, this is basically a rescaled, you can rescale the NP-complete subset sum problem to be an exponential size instance of the K-sum problem. And so it follows from this rescaling that if the exponential time hypothesis is true, then the K-sum requires n to the omega k time. Okay. Now the conjecture is this K-sum conjecture is much stronger, that it requires exactly n to the k over 2 time, but n to the omega k has a number of the same consequences that the strong conjecture would have. Okay, just a little bit weaker. So the idea is we can use these kind of standard reductions using sparsification and the standard technique to show that under ETH, subset sum requires exponential time, and then do this split and list reduction from subset sum to a mildly exponential 2 to the n over k size instance of the K-sum problem, and then a better than degree k algorithm for K-sum, much better than degree k, when combined with this would give us a 2 to the little o of n algorithm for the subset sum problem, and hence for satisfiability. Okay, so so that was like one of the starting points of this kind of merger of these different strands into fine-grained complexity. Since then, there have just been so many textbook problems that, based on some of these a small number of conjectures, the complexity would be exactly classified. Okay, so so as I said, these are, I should say, they're hypotheses rather than conjectures. Not sure that they're true, but they show a common algorithmic challenge that underlies progress on a whole bunch of seemingly unrelated algorithmic problems. Okay. And I'll single out Virginia Vasilevska Williams as like kind of the leading researcher in this area, but there are so many other people doing exciting work that I don't have time to mention. Okay, and I was going to talk about my own work, but just there's this problem, orthogonal vectors, that many of the SAT hardness results go through, and then you get like hardness for all sorts of natural probably. You open up your algorithms textbook, and you look at, especially under dynamic programming, a lot of the algorithms that you see have been shown that if you could improve them, you would actually improve the SAT algorithms and refute either the exponential time hypothesis or strongly exponential time hypothesis. Okay, so if these hypotheses are true, then we get a really detailed picture of the complexity, both of hard problems and of problems with NP. Okay. And we get a lot of insight into the kind of structure of instances that are likely to be the hardest problems for satisfiability. If the conjectures are false, well, like if the exponential time hypothesis is false, what we said is we get sub-exponential algorithms, not just for SAT, but for all CSP problems, and the scope goes on beyond that. So a lot of the NP-complete problems would just become all simultaneously sub-exponential. If strong ETH is false, I don't have a lot of algorithmic consequences for that. So I'd be interested in people coming up with algorithmic consequences if strong ETH is false. A lot of consequences if it's true. However, another interesting indirect consequence is that if these are false, we get improvements in circuit lower bounds. And this builds on the connection by Ryan Williams between circuit sat and circuit and lower bounds for circuits. Okay. So one statement of this type of result is by Jahanju, Miles, and Viola. They say if the exponential time hypothesis is false, there's a function in e to the np that requires superlinear size circuits. Proving a superlinear size lower bound for circuits is a major challenge in complexity theory. If the strong ETH is false, it's a little bit weaker. You only get a linear bound for series parallel, superlinear bound for series parallel circuits. Okay. It would be nice to put these lower bounds in a smaller complexity class. E to the np is still a little bit high up there for my taste. Okay. Well, why should anyone even think that exponential time hypothesis and strong exponential time hypothesis are even plausible? Because we have these sat solvers that are solving instances with millions of, really quickly on instances of sat with millions of examples. How could anyone argue with a straight face that sat is really hard? And what I want to say is these hypotheses are about the worst case time for sat. And the results, the heuristic results, are really about typical instances that come up in certain applications. And they don't actually generalize even to instances that come up in other applications all the time. It's not always easy to map your application to a kind of sat that's easy to solve for these with these solvers. That's an art. Representing your instance as a sat problem is an art in itself. Okay, and I'm sure lots of people here know that so well, and our masters did that. Okay, so and average case in complexity of sat is also really different from the worst case complexity. Okay, so and as I said, we can make this precise by looking at resolution proofs, because most of the current, even the current generation of sat solvers can be simulated on unsatisfiable instance by resolution proofs, where the size of the proofs is roughly the same as the time that, or a lower bound on the time that the sat solvers will take. So, so can we show that exponential time hypothesis and strong exponential time hypotheses are true for these kind of resolution proofs? Pavel Pudlak, with some prompting from me, show that this is true, that even the strong exponential time hypothesis is true for tree-like resolution proofs. That was like generation 1 of sat solvers. Chris Beck and I show that a similar thing for regular resolution proofs. And unfortunately, that might have been okay as a lower bound in strong ETH for generation 2 of sat solvers, but generation 3 using like clause learning already goes beyond regular resolution. And so we'd really love to have a similar result for general resolution lower bound. The best lower bound I know of for general resolution is in the same paper with a lower bound of 1.5 to something approaching 1 as k grows. Still shows like the exponential time hypothesis is true and gets pretty close, but we have a gap between exponential time hypothesis strong. Yes, there was a question.
The question is with regard to alpha. What is alpha in there?
Okay, so alpha in our proof, I think it's like an 8 or something.
Okay.
It's not, it is a little bit different in the 3 results, but it's just like some fixed number.
Can I ask a follow-up?
Yeah.
So I was interested in whether ETH or, strong ETH can be used as a way to rule out certain parameters as explanatory of the power of CDCL SAT solvers. And I saw an earlier result you had where it was shown that even if, I don't quite recall the result, but even if the tree
maybe
with the,
this is the Lokshanov, Marx, and one other person result.
right.
Yeah. So, and the one I stated was for independent SAT, but they have very similar results for variance of SAT.
And so that would conclusively show that certain kind of quote unquote natural parameters may not be good candidates to explain the power of CDCL.
Right. So, and I, so again, this is complex, making the assumption that, they say that you can't improve those, you can't improve the running time in terms of those parameters as without improving the running time in general. That doesn't mean absolutely that these SAT solvers haven't done that. So, so maybe something that we should try to work on is to show that, is to try to show a proof complexity lower bound for instances with bounded tree width.
Yeah.
I think that would be a really interesting result. So can we show that, here's an instance with tree width, for any tree width, we can like come up with an instance of that specified tree width where the smallest resolution proof is exponential in that tree width.
Right.
I don't think anyone's done anything similar. Correct me if I'm wrong. If there's someone who's done something similar, they're probably in this meeting. So please chime in. Okay. And so saying like the value of these hypotheses isn't because I believe that they're true, is because they summarize the state of the art on important problems, sort of like give a distinction between incremental progress and fundamental progress on the different problems. They unify progress on a wide variety of algorithmic problems that you wouldn't think are connected, and identify common challenges in coming up with algorithms for these different problems. They link complexity theory and algorithm design and allow really precise statements about can we formalize our intuitions about what makes instances and problems easier or harder. And I apologize for going over a bit.
Thank you for the talk. So clap on behalf of everybody, and so let's open the floor for questions. There's nothing in the chat or the Q&A, so either speak up or type something in.
So I have a comment.
Yeah, go ahead, Vijay.
Yeah. So we recently used strong ETH to show that a reduction from the theory of equality and uninterpreted function symbols to SAT the best you can do is n log n. So the theory of equality and uninterpreted function symbols is just quantifier free, that is. It's just, functions and constants and equalities between them, right? So you can use this in verification for many settings. And the way you usually solve such formulas is by doing an Ackermann style reduction to SAT. That's one way to do it. There are other ways. And we showed that you cannot do anything better than n log n if strong ETH is true. So I just wanted to let you know
that sounds
example.
Great. Yeah. So
I can send you the paper offline.
Please do. So I may have some related work for similar problems within polynomial time. We're looking at like the complexity of first order problems where you have like equality between variables.
Yeah.
So and also with Marvin Kuhneman and a bunch of of UCSD students, I'm also been looking at the complexity of logics where you have inequality, total orders between variables, and relating those to satisfiability and strong ETH. I'm a little bit impressed with your result because you're somehow getting an assumption about SAT being hard and getting that to be a barrier to reducing to SAT rather than reducing from SAT.
Right.
That's kind of counterintuitive how you do that. So I'm interested in
Yeah, now I'll send the paper in.
yeah. So is it like
there's a comment? Oh, sorry. Go ahead, Russell.
This would give a really good reduction from SAT to itself?
No, I think we use this Traxler paper, which has a. Let me. I'll have to now remind myself of this.
Anyway,
Yeah,
please send me the paper, or maybe since other people might be interested, you could also put a link in the chat.
Yeah,
if you haven't already.
Yeah, I will.
See, there's one thing in the chat.
Yeah, Stefan Sider has a comment in the chat. We know that unsatisfiable formulas have resolution proofs that is of size that is FPT and the tree width of the primal graph, but the question is open for the tree width of the instance graph.
Right. So saying that there might not be, I was asking for a lower bound in terms of the tree width. So first, which graph we're talking about is a little bit ambiguous. So we can ask the same question for different kinds of related graphs to the instance. I was asking for a lower bound, so it's interesting to start first by saying, is there an upper bound that matches the best algorithms? Can the best algorithms for the restricted tree width case actually be simulated by equivalent size resolution proofs? Is that what you're hinting at, Stefan?
Yes, I think that's correct. So it's relatively clear, I think, for the primal graph where we have the variables are the vertices, and you have an edge whenever two variables appear together in a clause. That's this very basic graph model. There, it's easy to transform any algorithm that solves the SAT problem on this instance, that it can also output a resolution proof as a witness. That's relatively easy. But if you now look at the incidence graph, which is this bipartite graph between variables and clauses, then the question is open. We don't know whether even such instances have resolution proofs that are FPT in the size, FPT in the tree bits of this incidence graph. Not speaking about an algorithm that actually finds the proof.
Right.
So Russell, I posted the paper and the link to a talk by Antonin on this one.
Great, thank you. Okay. So Albert has a question. So maybe you want to just say your question.
Yeah, so my question is whether ETH has anything to say about the permanent of n by n matrices.
Yeah, so there's a similar sort of exact complexity of counting problems, and there are lots of really nice connections. So I was looking at this a while ago, and I don't remember who exactly did what in this area, but there is actually a very well developed kind of analog of ETH for counting problems, including the permanent, and there may be like we may from ETH hardness, there may be a loss of a log n in the exponent. I'm not sure. So it might be that ETH implies that you can't compute it in time 2 to the little o of n over log n. So there's like if you look at I said everything is kind of like linear, but if you look at the reduction from sat to permanent, that's the standard proof of, from counting sat to permanent, that's the standard proof of Sharpe completeness, is not actually linear time. But then there's some very clever roundabout methods to get better lower bounds on, better conditional lower bounds on computing the permanent.
We could even use sub-exponential reductions, and that's a completely
Yeah,
unexplored thing.
So the ones I know use techniques like polynomial interpolation rather than sub-exponential reduction. So they're using Turing reductions rather than mapping reductions to get sharper bounds. But it's been a couple of years since I read these papers, and so I'm not remembering the details.
There's another question in the chat window from Isrupik asking, is there an analog for K quantifier QBF?
Yeah.
E.g. that you need, go ahead.
Yeah. So Ryan and Rahul Santanam, I think, had the first papers on the analogs of exponential time hypothesis for K quantifier QBF. For strong exponential time hypothesis, if you've got quantifiers, so the thing is, a lot of the improvements that you get for K quantifier QBF, you would intuitively think the hard cases are where you have an existential n over 2 variables followed by a universal n over 2 variables followed by the inside of the formula. But actually, if you think about that for a second, you can do exhaustive search over the outside variables, and then you've reduced to a SAT problem on n over 2 variables. And so whatever savings you get for SAT, you can kind of translate to this kind of balance case. And so the trickiest cases involve quantifier structures that are not at all balanced, and trying to reason about those. And it does get complicated. I had some work with Chris Calabro and Mohan, and then there was this paper by Ryan and Rahul. And again, even the results in our paper, I don't quite remember at this time. So maybe Ryan could save me and tell me what the state of the art is here.
So Paul commented on this.
The state of the art of what exactly? Sorry, I was away from the computer.
The exponential time conjecture of quantified Boolean, truth of quantified Boolean formulas.
Oh, right. So there is a for all exists version of Seth. If Seth is false, then this is false. As you increase more and more quantifiers, the problem actually gets easier. The more alternations you got, the faster the algorithms known can run. So it's fairly counterintuitive from that perspective. I mean, that's more or less a summary, but
yeah.
So Paul had a follow-up comment too.
Okay, so I think this is a different comment. Yeah.
Okay.
But I'm still trying to parse it. So Paul, could you just explain your comment? Okay. Okay, so Paul's having trouble unmuting, so I will try to read it and try to understand it. Okay, so So I guess, okay, so yeah, so the some examples where we're able to show that the limiting constants are kind of identical for strong ETH, the standard strong ETH, and variance is we're able to show that for the unique SAT case that you get the same constant, and for the bounded density case. Okay, yeah. So there's so that the paper. Okay, so so I should say there is a paper. There aren't so many results that say, you know, we would want results that say if the strong ETH hypothesis is true, then the constant for independent set is exactly this number. The constant for this problem is exactly this other number, and so on. So, you know, it would be great to have some kind of version, you know, exponential time analog of the unique games conjecture, where if you assume that conjecture, all these other constants actually are kind of mathematically well defined, and you know exactly what you're shooting for. We don't have that. There's a paper by a very large number of authors, including Daniel Luxtonov and Mohan Paturi, and I'm forgetting exactly who else, that gives that does give for some examples that strong ETH would imply that certain problems had constant 1. But I'm not remembering the exact link. The paper that Sybil points to, I think, is like one in a series, but I'm not sure whether it is the first link in the series. As a book chapter, it's probably further along, and maybe combine several conference papers would be my guess.
All right. So thank you again, Russell. There's another talk in about 7 minutes, so we probably need to wrap things up. I believe there's a fellows talk in 7 minutes. So thank you again, Russell. And
thank you. On
behalf of everyone else, clap. And thank you also, Jack. So it's been a very nice session. So I guess that there's some chance to go to GatherTown, I think. I don't know what the link though, but if you want to continue talking afterwards, maybe someone will post the GatherTown link, or you guys know how to go. So otherwise, I think we're done. Thanks.
Thanks.